All right, guys, so we're going to pick up where we left off yesterday. I want to go back and hit the high points again. Remember, John Dalton, he had 5 postulates or 5 hypotheses that we talked about. Remember, we talked about what we want to do with this is know, was he telling the truth? Excuse me, not was he telling the truth. Was he accurate or was he not quite accurate? Was he right or was he wrong? So I know we did. I just want to hit him again. High points again. High points. He said everything's composed of atoms. True or false? True. All atoms of the same element. So all carbon atoms, every single one of them are the same in size and mass. That's false. And what was the thing I told you that makes that not true? Isotope. Isotopes are the same elements with a different Y. Very good. Different number of neutrons, okay? I'm going to go ahead and tell you this today. We're going to get into We're going to get into this topic next chapter. Isotopes have different masses. Does anyone know what an atom is called that has a different size? Just another I word. You may have heard of it before. It's a lot shorter. An I? Another I word? An ion. I'm sorry, I didn't hear you. Okay? An ion. That's right. Okay? And we'll talk about what ions are in the next chapter. But just know that ions are also real, and they are different sizes, where isotopes are different masses. Okay? True or false? Atoms cannot be subdivided, created, or destroyed. That's false. Very good. Then we said that atoms of different elements, simple whole number ratio is true or false? True. And then in chemical reactions, combined, separated, rearranged. That is also true. Very good. Then we talked about, and again, this is the words where we said he was right and he was wrong. Did we get into this? Well, where we talked about this. The percent of an atom's mass is contained 99% where? In the nucleus. But the nucleus is only how much of the space? Less than 1%, okay? All right, we talked about that was a picture of it. We talked about surrounding the nucleus are negatively charged electrons, protons, neutrons, electrons, subatomic particles. Then we compared the masses. We got to this part, right? No, did we get to this part? That right there. Okay, so we're gonna. So here's the first thing we'll talk about. So surrounding the nucleus. Okay, we're not there yet, so we're good. Surrounding the nucleus is a region occupied by negatively charged negatively charged things called electrons. Okay, protons, neutrons, and electrons. Highlight or circle that word: subatomic particles. Now, this is something I think you know, but I want to stop and just make a point of emphasis here. On the test or on worksheets or in the language that we use, if you ever hear me say the words subatomic particle, I'm talking about those 3 things. So it's just like a vocabulary word. What are the subatomic particles? Protons, neutrons, and electrons. And just for emphasis, if you want to do this, protons are positive, neutrons are neutral, and electrons are negative. Very good. Okay. And every year, people always mess up neutrons and they call them negative. Again, neutrons are neutral. The first 5 letters are the same. N-E-U-T-R. Neutron and neutral. Okay? It does make sense. So here's the thing that I want to talk about. So I want to talk about the 2 outside things. The name and then the masses. So electron, protons, and neutrons. So let's look over there at the masses. The mass of an electron is 9.1 times 10 to the negative 31st. Is that a really small number or a really big number? That's super, super, super small. So for perspective, if I wanted to get rid of scientific notation and write it in expanded form, first of all, which direction does the decimal move? Left. And how many zeros would be to the left of that 9? 30 of them. Because I already moved it one time around the 9. 30 zeros in front of that 9. First of all, I'm not writing that number. Second of all, is that really tiny? Okay, that's really tiny. So the middle column is the important part. Relatively, what is the mass of an electron compared to protons and neutrons? No, the middle column. Well, sorry, there isn't a middle. Sorry, that right there. What's the mass of an electron? 0. There isn't a mass of an electron. Exactly. So why is that true? Why do we say the mass of an electron doesn't exist? Because when you compare it, let's look at the other 2 numbers again. So proton and neutron are very, very, very similar. Would you agree to that? Okay. But the scientific notation form has a negative 27, which means there's how many zeros left of the 1? 26. Now, So here's the deal. If I take one electron and I remove it from an atom, and I subtract that number, the top number, from the mass, are you going to be able to tell that the number went down? Not at all. What if I take an electron and I add it to it? Are you going to be able to tell the mass changed at all? Because it's so much smaller. So we've got 30 zeros in front of the 9 versus 26 zeros in front of the 1 for the protons and neutrons. So it's so much smaller that you can add a ton of them or take a ton of them away and you'll never be able to tell the difference. Okay? It's kind of like our national debt. We're $20 trillion in national debt. If I said, here's a penny, is that going to help it at all? You people. Holistically, would it help? No. Okay, it's not gonna make an impact at all. And that's kind of the same concept here. The numbers are so small that when you take or add one away, you're not really going to be able to tell a difference. And so that's kind of what it's referring to here, is that the mass comes from the protons and the neutrons. All right, so let's talk a little bit about history. There are 3 guys we need to know from the historical standpoint. So cathode rays and electrons. Experiments in the late 1800s showed that the cathode rays, and I'm going to show you in a picture in just a second, so I know you don't know what that means, were composed of negatively charged particles. And what did they call those particles? Electrons. Okay. So who was the person that did this? And this is what the next slide is. So the 2 guys we need to know to begin. Remember that we said there's 3 of them. The first guy is J.J. Thomson. Okay. Here's what I need you to know about him. You need to know 3 things. You need to know his name. You need to know what experiment he did and what he discovered. So J.J. Thomson used what experiment? The cathode ray tube. Okay, and he discovered the electron. Okay, the charge to mass ratio of an electron. So J.J. Thomson used the cathode ray and he discovered the electron. There's one more thing I want you to write out beside J.J. Thomson's name. And that was the name of his model of the atom. And some of you have seen this before. The plum pudding model. The plum pudding model. Now, this is a British dessert. And the weird part is it's not even a plum. Excuse me, plums aren't even in it. And it's not even pudding. It's like a muffin cake. Yeah. Okay. Again, where this name came from, I don't know. British people, right? God. Smell bad and eat fish. All they do. I'm just kidding. I'm just making stuff up. They have cool accents. I appreciate the accents. So this is what he called his model. And literally what it is he said it was a sphere. Okay. Some of us might be way back when. All right. What he said is an atom looks like. He said it's just this round sphere with these little bitty things stuck to the outside of it that are negative charged particles. So imagine like a blueberry muffin. And imagine like seeing the blueberries at the top of the muffin. Those are like the negative particles. You all right? Did you freak out for a second? So he called it, again, the plum pudding model is what he called his model. So the second guy we need to know is Robert Millikan, and that's his picture at the bottom. J.J. Thomson is at the top. Robert Millikan, again, his name, what he did, and what he discovered. Robert Millikan used what experiment? The oil drop, and what was he able to determine? The charge of an electron. Now, before we go any further, what is the charge of an electron? Negative. Okay? And I'm going to show you a picture of both of these in just a second. Okay, I'm going to show you a picture of them. So here is a picture of the cathode ray experiment. Now, this is not the greatest picture. I have another picture that's not in your notes you're going to see in just a second. But I want to kind of talk about this in essence. What is a voltage source? What is a source of voltage? It's a battery. It's a battery. Or it's a wall outlet you can plug in. So what happens is they had a battery and the electric current went through this tube. And inside where this yellowish color is, there was a gas. This gas conducted electric current, which means what? Could the electricity go from one side to the other through the gas? This is the symbol for a battery. In physics, if you ever take physics, that is the symbol for a battery. Okay? This is a tube. So what happened is the electricity had the ability to go through this thing, through the gas. But this is what they did. This is how they figured out that there was something charged on those in that gas. This is what happened. So underneath, this kind of was like one of those tape measures, you know what I'm talking about? So they put it underneath this cathode ray, and what happened? Look at the green light. It pulled it down. It deflected it down. So what happened is that it attracted those gas molecules down here, so the electricity essentially just followed the flow of the gas. So he was able to prove that because there was some sort of attractive forces between the gas in the tube and this magnet, there was something charged on those atoms. And so this was how he discovered that they were charged. Okay, that's how he discovered the electrons. Now, the oil drop. It's not as fancy of a picture, but it makes sense. So first of all, what are those little yellow droplet-looking things? Oil droplets. Now, on the right, it says it's an atomizer. I'm not exactly sure what that means, but what my perspective is that he took the oil and he turned it, instead of like a goopy glob, it was like atoms of the molecules, if that makes sense. Okay, so it was really, really small. And so this one happens. These oil droplets fell through this red plate. Now, first of all, what is that red plate? Okay, so charged metal plate, but this is the important question. What is the charge of that metal plate? Positive. Okay, now, in between the blue and the red, there was two things. There was, on the left, there was an X-ray source that was called ionizing radiation. And what that did is when he put in that X-ray, it hit those oil droplets and it charged them. Okay, which means it gave a positive or negative charge to it because there was so much energy whenever it hit it. Okay, anybody ever had an X-ray? You know, like your bones show up on the plates. That's kind of what happened. He hit those oil droplets with so much energy that it gave it a charge. Okay, on the right-hand side of the middle, there's a microscope. What do you think the purpose of that was for? So he could see it. He could watch what was happening. And here's what happened. At the bottom of this thing, there was another charged metal plate, but what was the charge of that thing? Negative. All right. So we know that electrons are negative. So when he ionized those oil droplets, think analytically here, where do you think those oil droplets went? Do you think they went back up to the red, or they kept falling to the blue? Why did they go back up? Perfect. And that's why I asked that question a second ago. Why does it matter if they're positive or negative? Why does it matter where they are? So an electron is negative. Well, the red plate was positive, and what do opposites do? They attract. Okay, does that make sense? So these oil droplets went down, got ionized, and turned around and went back up. Now, I have a kind of a follow-up question, and this has nothing to do with the experiment, but I just want to kind of talk out loud. Do you think people could have criticized him had he taken the red plate and the blue plate and swapped them? What do you think the flaw could have been? Okay, why would they have kept just going straight down? But what would be the flaw in that? How could I say, if that's true, you're right, it would pull it down. But what could I say to you like, no, that's not true because of this? Gravity. Perfect. Naturally, if I drop some oil from here, where's it going to go? Down. So if you have the positive plate at the bottom, then that would make sense. It just comes through and it pulls it through. But there are two alternative versions there. Yes, the plate pulled it down, but did gravity also have an effect on it? But when he looked and that positive plate was on top and those oil droplets started going back up, was that solely due to the magnetics? Yes, and that's kind of how he was able to prove that electrons were negative because they were attracted to that positive plate. And so this is how he was able to determine the charge of the electron. That is Millikan's oil drop experiment. Okay? So the third and final guy that you need to know is Ernest Rutherford. Okay? Two of his buddies that helped him out were Hans Geiger and Ernest Marsden. Has anybody ever heard of Geiger before? What's it used for? What did he do? He invented the Geiger counter that counts radiation. Have you ever heard maybe, possibly? Okay. He is kind of famous for that. So before I tell you what he did experimentally, let me give you a real-life example of what he did. Imagine if we went outside and I handed you a BB gun. This is real life, okay? and I said, I want you to shoot that piece. I want you to shoot a piece of aluminum foil. Okay, just shoot at it. What would you expect to happen? It'd go right through, right? Would any of the BBs just disappear? No, they'd all go through. Imagine, like, if we had kind of like a styrofoam block behind it. If we shot into it, we would be able to go count them all. So, in a very, very small micro scale, that's exactly what he did. But obviously, he didn't use BBs and he didn't use aluminum foil. But what he did use is he used the gold foil, which is the exact same thing as aluminum, but it's not aluminum. It's what? Gold. So what he did, Ernest Rutherford, he used the gold foil experiment. Okay, that was the thing he used. And he was able to find the nucleus. Okay, so Ernest Rutherford, gold foil experiment, found the nucleus. And here's how he did it. Imagine if I handed you that BB gun and you shot that aluminum foil, and all of a sudden the BB started bouncing back at you. Would that freak you out? Yeah, because that doesn't make any logical sense to us at all. And that's exactly what happened to Rutherford. He shot particles at gold foil, and they bounced back at him. Now, not all of them, but some of them did. He said, how in the world can you shoot something so small at a piece of gold foil? Why is it bouncing back at me? So he said, there's got to be something in there that's making them bounce. So not only were they reflecting at him, they were also deflecting. What does deflection mean? Like it changes its angles, right? So this is what he saw. So he shot these particles. You'll have this picture, right? Okay, do me a favor. Draw, hold that thought for just a second. Need to look something up, because I don't want to get it wrong. Can't ever remember the symbol. It doesn't matter. These are alpha particles. And alpha particles are positive. Well, now that I've told you what he did and what he discovered, again, what did he discover? The nucleus. He shot positive particles. So, using your brain, why do you think that positive particles would either deflect or bounce back when they hit that gold foil? Say it again. They don't attract. So what was those alpha particles hitting when they went through? They were hitting the positive nucleus. Now, we've already discussed this. What two things are in the nucleus? Protons and neutrons. Protons are what charged? Positive. Neutrons are neutral. So the entire nucleus is what charged? Positive. So positive things hitting a positive thing, it causes it to do what? Deflect. Which is exactly what happens in this kind of picture. So this really, really, really tiny nucleus, if it was at the perfect speed and the perfect angle, would slam into that nucleus, and it would cause a deflection. Okay? Does that kind of make sense logically? So this is how he found the nucleus. I want to read you this. This is out of the textbook. It says that, first of all, he said, imagine if you had fired a 15-inch artillery shell at a piece of tissue paper and it came back and hit you. That was what he wrote in his thesis whenever he was going through this. I mean, imagine that, an artillery shell bouncing back at you. That's crazy. There was one last thing I wanted to read to you. He said Rutherford had discovered that the volume of a nucleus was very small compared to the total volume of the atom. So it's really, really tiny, which you already know that. This is what he said. He said, in fact, that if the nucleus were the size of a marble, everybody knows what a marble is, right? That the size of the atom would be the size of a football field. So think about the middle of the 50-yard line on a football field, and there's a marble sitting on it. The rest of the field is the size of the atom. And the marble weighs the most. Everything else is empty space. And you have these electrons zooming around at the speed of light that you can't even see. Okay? A marble on the 50-yard line in the middle of a football field. That's the size of the nucleus. The football field is the size of the atom. That's how the size comparisons work. Does that make sense? Logically, it doesn't make sense. Like, how are we held together by all of that stuff? That's the part we're trying to figure out. We don't really know. Why is there so much space? Okay. So again, it was kind of interesting, and then it goes on to say, and we're going to talk about this in the next chapter, because it follows up by saying, well, where are the electrons? This question was not answered until Rutherford student Niels Bohr proposed a model in which electrons surrounded the positively charged nucleus as planets surround the sun. And again, we'll talk about that chapter 4, and I'm going to go ahead and tell you Bohr was wrong. They are not like planets. Okay? Why? Okay. Well, it's even more exciting what it is, actually. So, except for the nucleus of the simplest type of hydrogen. Now, I'm going to go back and I'm going to show you what we wrote yesterday. If I can find it. There it is right there. Nor, read me that sentence again. Except for the... Pause right there. Yeah, no, keep going. Sorry. Pause. 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 All of them except for the simplest type of hydrogen have protons and neutrons. Who is the simplest type of hydrogen? Protium. I would write that down beside that. So, protium is essentially one proton. Okay? There are no neutrons. Protium is one proton, no neutrons. So everything else has some neutrons. A proton is a positive equal to the magnitude of a negative charge. This next bullet, put a big, huge star beside it. I need you to know this next bullet right here. Atoms are electrically neutral because they contain equal number of protons and what? That is very, very key. And let me explain how we would know that. What is the sign of a proton, or the charge of a proton? What is the charge of an electron? So if you have the same number of positives as you do negatives, what do we call that? It's an N word. Neutral. Okay. Is it possible to have different number of electrons? Yes, we just talked about that. What's that I word? No. An ion. Okay, we'll get into that in the next chapter. Okay, so a neutron is electrically neutral. So neutrons have no impact whatsoever over the charge of an atom. And again, we'll talk about that in the next chapter. Right up here, it's actually in orange. Except for the nucleus of the simplest type of hydrogen, that is protium. Protium is the simplest type of hydrogen because it does not have any neutrons. Okay? So the nuclei of different elements differ in their number of protons. Think about that one more time. Different atoms have different number of protons because if we look up here on the periodic table, all 118 of them, right? They all have different numbers of protons. That's how we identify them. And that's what this slide is telling you. So if you don't know those bottom two, please make sure you know that. So the nuclei of atoms of different elements differ in their number of protons, therefore the amount of positive charge they possess. Thus, the number of protons, put a big star beside that, the number of protons determines the atom's identity. So if I said, who is an atom that has 20 protons? Who would that be? Calcium. And all you do is look up there and find number 20. Okay. Now, does every calcium have exactly 20 neutrons? What do we call those things that have different number of neutrons? An isotope. Do all calciums have 20 electrons? No, and we'll talk about that in the next chapter. We'll talk about ions. So if you change the number of protons, you change the element. Okay, period, point blank. No questions about it. If you change the protons, you change the electrons. Or you change the element. Now, this is where it gets kind of weird. And all I need you to know is that last word in purple and know the definition. What is a nuclear force? What do you think a nuclear force is? It's kind of the opposite. It's the force that holds the nucleus together. Okay? What two things are in the nucleus? So basically, it's the force that protons have on each other, the force that neutrons have on each other, and the force that neutrons and neutrons have on each other. So that second to last bullet, it says the short-range proton-neutron, proton-proton, and neutron-neutron forces that hold the nuclear particles together is called the nuclear force. So again, the thing that holds the nucleus together is called the what? Nuclear force, which is a beautiful picture right here. Okay, so that thing on the right is what's holding all that stuff together. But I have one question. What are all the charges of all of those red things? They're all positives. And you've already told me that opposites attract, but what do like things do? Repel, deflect. So how can all of those protons that are all positively charged stay stuck together? Okay. The nuclear force is stronger than the repulsive force. Okay. So they can stick together because that force is stronger than they are being pushed apart. Okay. The radius of an atom. Now if I said what's the radius of a circle, what is that? Half the diameter. Okay, what's the diameter? If I drew a circle, what's the diameter? It's the whole width, right? So the radius of an atom is the distance from the center of the nucleus to the outer portion of the electron cloud. Hint, hint, wink, wink. You need to know that. That's a TQ. That's a test question. No, sir. Absolutely not. Absolutely not. The first one. The last bullet's also a TQ. That one's an easy one. I'm going to go ahead and tell you. What is the unit atoms are measured in? Just know it is a fact. I'm telling you that's a TQ. But here's the question. It says the radius of an atom is the distance from the center of the nucleus to the outer portion of its electron cloud. If I handed you a ruler, obviously, if it was small enough, could you do it? Why can't you? Yeah, cloud. The electron cloud. Do you know where the edge of a cloud is? Is it always changing? So how do you know where the end is? You don't. It's not there. It's an interesting question. So because atomic radii are so small, they're express units. So here's what we have to do. Yeah, this is where you're going to get mad at me. It kind of gets back out of order. I apologize. So the definition that I just gave you is it's from the center of the nucleus to the outer portion of the electron cloud. But you just told me that you have no idea where the edge of the cloud is, so how do you know where to measure it? So here's an alternative definition. I'm going to pause for just a second. I want to see if it's on here. No, it's not on here. So here's what the definition could also be. It is half the distance between the nuclei of two identical bonded atoms. So let me talk about that in picture terms. The last part. Two identical bonded atoms. Are there two atoms in this picture? Are they identical atoms? The radius is half the distance between the two nuclei. So, do you agree that the nucleus of this atom is right there in the center? Do you agree the nucleus of this atom is right there in the center? Is there a distance between those two things? So what's the radius? Half that. So that's an alternative version that some textbooks, some people use, because technically it's a little more accurate. And the reason why it's more accurate is because, do you know where the edge of that electron cloud is? It's hypothetical, it's potential, it's probable, but it's not accurate. So this is the definition that sometimes people do use. One more time. It's half the distance between the two nuclei of identical bonded atoms. So if I change these to two oxygens, could you do the same? If I change it to two carbons, could you do the same? Okay, so that's kind of the whole essence behind it. It's half the distance between the nuclei of two identical atoms that are bonded, or two bonded identical atoms, however you want to phrase that. So it's half the distance between the nuclei of two identical atoms that are bonded. Now, next chapter, it may not be next, it may be the one after that. I can't remember which chapter it is. We're going to talk about atomic radii as far as a trend and how it works. In fact, it's up there on that poster up there on the middle right. That poster is always going to be there. So, this is what it is up here on the board. So if I asked you guys what region of the periodic table has the smallest atoms? Where would you say? Top right. How can you tell they're the smallest? Because those dots are really tiny, right? They're so small. What part of the periodic table has the largest atoms? Sir? Of two identical atoms. Yes, that are chemically bonded. Where are the biggest atoms? So here's kind of what I want you to do on the slide. As we move to our right, what happens to the size? This is a foreshadowing. We're going to get to this later. And I'm going to teach you how and why. So if you can just memorize that as you move across, they get smaller, you're good for today. And one more thing. As we go down, what happens? They get larger. Or bigger, however you want to say it. Doesn't matter. That's just the fact for the day. Well, to be honest with you, the 7th row, francium, the very bottom, it's not even on there. So I don't honestly know what the biggest one is. I think it is the largest. I'd have to look it up to tell you the honest truth. I'm going to throw one curveball into your brain for just a second. This is something to ponder as we go throughout the day, or as you go throughout the next few chapters. I'm going to circle this row right here. Can y'all see that? I know it's kind of hard to see. You don't have to do this. I'm highlighting it for a reason. So, what number is potassium on the far left? Number 19. All right. What number is Kr on the far right? 36. Do you agree that's the number of protons in each atom? All right. So think about this. If you have 19 protons, and if it's neutral, how many electrons would you have? 19, right? Because you have the same number of positives as negatives. So you've got 19 electrons on the left. Over there on the right, you've got 36 protons and 36 neutrons. So let me ask you, numerically, which one is greater? 36. Well, here's a weird question. How can an atom that has 36 protons and electrons be smaller than something that has 19? It's an interesting question, isn't it? It's a really good question. Ponder that. There is an answer, and we will get to it. I think they don't know those. And this is has nothing to do with all this. The reason those are hollow, there's something called half-life, which is how long it takes for half of the substance to decompose. And some of those half-lives of some of these man-made elements are like fractions of seconds, which means they only exist for very short periods of time. So they have never been able to take an atom and figure out its size because they don't last long enough. Does that kind of make sense? And honestly, that's why almost that whole entire bottom row is missing. Because if you notice on that periodic table over there, you can barely see it. Let's look over here. Look to your right. That back one back there, that whole bottom row is those like hollow letters, which means they're all man-made, which means they only exist for milliseconds or picoseconds. Like, they are very rare to find them, and so they don't know how big they are because of that. They know they're really small, but they haven't figured it out yet. They either take things and slam them into each other and it creates stuff. Like, basically the atoms hit with such force, they combine into something new. Or they take atoms and they hit them so hard that they break into different pieces, and you combine them that way. Okay. All right, the last picture I want to show you guys, and we'll stop here. This is the exact same thing that you guys just looked at, but it's on a scatter plot graph, and you can notice is that all of the highest peaks are all group 1s. And if you go back up, notice group 1, right? They're all the largest. So as you move left to right, they all go down, and eventually it jumps back up. So, Seth, this answers your question. Not Seth, Harrison, this answers your question. Francium on the far right, it is one of the largest one. Yep. Yeah. And in fact, that's kind of weird. That's a great question. The data set uses colors derived from those of the plastic space-filling models developed by Pauling. The atomic radii values are calculated from values from that. Note there are no radius values can be found for a particular element if a radius has to been set to default value of 1 antigram, circle plotted. Okay. Yeah, the plot means they couldn't find one. They don't know the radius of it. To be honest with you, I don't know why they are different colored. That's a great question. I wish I knew that. If I had a hypothesis, it would be the fact of when they were discovered. Because if you notice, well, I don't even know about that. I don't know. That's a great question. You got me.